Next, we'd like to welcome Joe Luis Sabrino, presenting Dragon, distributed route aggregation on the global network.
Well, can everybody hear me? Yeah. Well, good morning. It's a pleasure to be at NANOG. I'm going to talk about distributed route aggregation as means to scale the internet routing system. This talk reflects joint work with Laurent van Bever, Frank Ley, and Jennifer Wexford. So, news from last year came to remind us that the internet has a routing system, that the internet routing system is engineered and has limitations. In August last year, the number of globally advertised IPv4 prefixes went past the 512K mark, which was the default forwarding table size of some routers. These routers could not cope with all the routes they were receiving, which event caused some noticeable outages in the internet. As a matter of fact, the internet routing system does not scale well. Most of the prefixes originated at the various ASs are propagated by the Border Gateway Protocol to all other ASs. So in this example, prefix 1000/16 originated at AS4 is propagated to all other ASs. The same is true of prefix 1100/16. It's propagated to all other ASs. Even prefix 1010/24, whose address space is contained in the address space of 1000/16, is propagated to all ASs. Take an analogy, however imperfect the analogy is, with road networks. A prefix is a set of addresses, that is a neighborhood in some city. Internet-style routing in road networks would mean that every crossroads in the internet would have a signpost for every neighborhood in the world. This is not realistic in road networks. In the internet, it takes a toll on performance or on cost. The growing numbers of globally announced IPv4 prefixes, or IP prefixes in general, overloads the forwarding tables of the routers, and it delays the lookup time of an address in those tables. It overloads the routing tables. It increases the BGP session setup time, and yields high churns and long convergence times. The lack of scalability also does not bode well for the future of the internet routing system. We are finally witnessing a transition from IPv4 to IPv6 prefixes. Without an addressing plan for IPv6 that takes into account routing scalability, many more IPv6 prefixes than IPv4 prefixes are potentially formed. At the same time, we see a momentum endowing BGP with security features. Secure BGP, in particular, requires authentication, online authentication and verification of routes. And this further burdens the routing processes. So Dragon is our distributed solution to scale the internet routing system. The basic version of Dragon consists of a filtering strategy that purges redundant routing information from the internet. It achieves savings on the routing and forwarding state on the order of 50%. Full Dragon includes as well an aggregation strategy that boosts the savings to about 80%. Significantly, Dragon does not require changes to the forwarding plane, nor does it require changes to the BGP protocol. It only adds new routing procedures to the routers that can readily be implemented in router software. We are implementing it in Bird. So, in the remainder of this talk, I will present Dragon. The art and the science of inter-domain routing lies much on our ability to relate global routing behaviors to local routing procedures. I will start with a global view of internet scalability. Dragon is our set of local procedures to realize that global view. It consists of a filtering strategy and an aggregation strategy. I will also present some performance results on Dragon. At a very high level, we aim for a routing system where the more specific prefixes are propagated only in the vicinity of the ASs that originate them. So in this example, prefix 1010/24, which is more specific than prefix 1000/16, is propagated from AS3 to AS2, but not further to AS1. In terms of forwarding, it means that data packets are forwarded along ever more specific prefixes until they reach the destination. So a data packet with destination address 1011 is forwarded at AS1 along prefix 1000/16. When it arrives at AS2, is forwarded along prefix 1010/24, which is more specific. This more closely resembles the reality of road networks, where signposts at the crossroads have coarse-grained information about faraway destinations and only detailed information about nearby destinations. But do we have reasons to believe that such a global view is possible in today's internet? And in hindsight, after the work on Dragon, the answer is yes. There is some implicit structure on the internet routing system that can be exploited, harnessed for scalability. There are two sides to this structure. First, many ASs buy connectivity from their providers. This establishes an hierarchy between customer and providers. That hierarchy is aligned with the prefix hierarchy in the sense that the more specific prefixes are originated by customer ASs, suggesting that they don't have to be propagated too far away from their provider ASs. The second aspect is that ASs that originate aggregatable address space are roughly clustered together. Routing information registries assign address space in a given geographic region, and ASs tend to connect to providers in the same geographic region. This is rough. Okay. So the challenge is, how do we realize this global view through automated local routing decisions? And this is challenging, especially given that the internet routing system is as decentralized as it can be. Each AS decides where to connect, whether at an internet exchange point, whether or not to multi-home. Each AS decides where to acquire address space from a regional or local registry from a provider, and each AS decides on its own routing policies, how to announce its address space, and how to treat the routes it receives from its neighbors. Okay? So Dragon is our set of procedures, local procedures, to realize that global view. Let's go to the filtering strategy of Dragon. The filtering strategy allows some ASs to filter the more specific prefixes while respecting the routing policies. Filtering a prefix means the prefix is not installed in the forwarding table, and the prefix is not announced to neighbor ASs. With filtering, we have a concern about the creation of black holes, happening when a data packet arrives to a router that does not have a matching prefix for its destination address. The packet will be dropped. Now, Dragon provably does not create black holes. Moreover, the filtering strategy must align with the incentives of the ASs. And we assume that among these incentives are the will to save on forwarding state and the will to forward data packets along the best possible route. Okay. The exchange of routing information is with standard BGP. I will exemplify the filtering strategy with this simple network with 6 nodes. Nodes represent ASs and lines represent adjacencies. A solid line represents the provider-customer adjacency with the provider always above the customer. Dashed line represents a peer-peer relationship. AS1 and AS2 are peers. AS1 is a provider of AS5. AS4 was allocated some amount of address space, which is summarized in prefix P. It's in there. AS6 bought address space from AS4, and that address space, that delegated address space, is summarized by prefix Q, which is more specific than prefix P. Prefix Q and P are propagated network-wide with BGP routes. A route associates a prefix. This works by itself, I'm so sorry. By associating a prefix to an attribute. So AS6 creates a route pertaining to P, which is called a Q route, a route pertaining to Q, a Q route, that it sends to its neighbors. I will assume the Gao-Rexford routing policies, which are believed to provide a baseline of understanding for how network operators set their policies. And these policies are based on just 3 attributes. The route can be learned from a customer, learned from a peer, or learned from a provider. The preference among routes just follows the flow of money. Given customer route, peer route, and provider route, I prefer the customer route because the customer is paying me. Then I prefer the peer route. Although the peer is not paying me, I'm also not paying the peer. And last, I prefer a provider route. The exploitation of routes is also consistent with the flow of money. Customers buy connectivity from providers, so all routes originated at customers have to be sent by the providers to all their neighbors. All routes arriving at the provider are sent to all their customers. So continuing with this example, the route sent by AS6 arrives at at AS3 and AS4. AS3 and AS4 elect a customer route to reach Q. So in this case, they send their packets directly to AS6 with the customer. And AS3 and AS2 re-announce the routes to their neighbors. AS2 receives the route from AS3 and AS4, and it also elects a customer route to reach Q. AS5 elects a provider route to reach Q. Since AS5 has no customers, it does not send the route to anybody else. AS2 sends the route, AS2 sends the route to AS1. When AS1 receives the route, it elects a peer route to reach Q. I think this works, okay. I'm sorry about this. So it elects a peer route to reach Q. It reaches Q via its peer AS2. So the final state for prefix Q is the following. AS2, AS3, and AS4 elect a customer route to reach Q. AS1 elects a peer route to reach Q, and AS5 elects a provider route to reach Q. The same process propagates prefix P network-wide. And this slide represents the final state for P and Q. The forwarding of packets follows the longest prefix match rule. So a data packet is forwarded along the longest prefix that matches the destination address of that packet. For instance, a data packet with destination in Q arriving at AS3 will be sent along the customer route directly to AS6 rather than along the provider route to AS2. Now, the goal of Dragon in this network is to forego Q as widely as possible and relying on the P routes to send traffic. Towards this goal, we'll work with the following code. The origin of P cannot filter. Any other node will filter Q if and only if the attribute of the elected P route is the same or preferred to the attribute of the elected Q route. This is reasonable from the point of view of a single AS. Filtering is good. It saves on the forwarding tables. And when I filter, I start sending data packets with destination Q along the P route, but the P route has the same or a preferred attribute than the Q route. So on filtering, I start forwarding packets along an equally good or better route. The checks here mark the nodes that will filter Q if they apply the filtering code. So the issue is, what's the global effect of one AS applying the filtering code? Let's suppose AS2 applies the filtering code. It elects a Q route, a customer Q route, and a customer P route. It will filter Q. On filtering Q, it does not send the route to AS1. So AS1 will be oblivious of Q, but it still forwards data packets with destination in Q along the P route, the one that was elected for P. If all nodes apply the filtering code, we arrive at this final state. In this final state, AS1, 2, and 5 forego Q. AS3, they have coarse-grained information about Q via prefix P. And AS3 and AS4 have detailed information about Q. They have a route for Q. Another way of looking at this is the following. Prefix Q is propagated only in the vicinity made of AS3 and AS4. I'd like to call your attention for two properties of this global state. First, it is correct. All packets are delivered to their destinations. There are no black holes. Second, the attribute of the route used to forward data packets is preserved. So, for example, you have here AS1 that before sent packets along a peer route. It still sends packets along a peer route, but now a less specific peer route. Such a state, where the attribute is preserved, is called route consistent. And in this particular case, the state that we have is optimal route consistent, in the sense that filtering by any other node will break route consistency. If AS3 were to filter as well, then data packets arriving at AS3 with destination in Q would be forwarded along a provider route rather than along a customer route. I will show you another example of the filtering strategy highlighting two aspects. First, filtering by one AS incentivizes the other ASs to filter as well. Second, there is an ordering for deployment of Dragon that is route consistent at all intermediate stages. Let's have a look at this example. AS2 is a provider of AS4, which is a provider of AS5, which is a provider of AS6. AS2 peers with AS1 and AS3. AS1 is a provider of AS3 and AS6. AS5 originates prefix P, the less specific, and AS6 originates the more specific one, Q. Again, checks mark the nodes that will filter Q if they apply the filtering code. Let's suppose that AS4 does apply the filtering code. Then AS4 filters. It does not send the route to AS2. So AS2 now resorts to the peer route that it learned from AS1. This state is not route consistent. AS2 is in a worse position now. But AS2 now has a double incentive to filter as well. On filtering, it saves on forwarding state, and it reverts to sending data packets to a customer rather than to a peer. So if AS2 filters as well, the packets go downwards in this line. Moreover, it's possible to choose which nodes, an ordering for the nodes to filter that is route consistent at all times. This is almost like substituting the wings of a plane while in flight. So the rule is, those that elect a peer or a provider route should be the ones to filter first, in whatever order. So here, the one that elects a peer route is AS3, should be the one to filter first. It filters, but the flow of packets is the same. And then among those that elect a customer route, they should filter top-down in the customer provider hierarchy. So a node should only apply the filtering code if its providers have already applied the filtering code. So AS2 is the one that has no providers there, should be the first one to apply the filtering code. The flow of packets remains the same. Then AS4, and then the flow of packets remains the same. Okay. Now, we don't have just two prefixes in the internet. In fact, we have more than 500K prefixes in the internet. These prefixes are logically organized in trees, where the provider-independent prefixes are at the roots of those trees. The filtering code applies between a node and the parent, between a prefix and the parent prefix in the tree. The parent of a prefix P is the more specific prefix that is less specific than P. Okay? We have shown that Dragon, the filtering strategy, is correct for the same routing policies for which BGP is correct. And if there is an additional property called isotonicity, then Dragon is optimal route consistent when all ASs apply the filtering code, and there is an ordering for deployment that is route consistent at all intermediate stages. Isotonicity is a talk in itself, but essentially it means that if one AS prefers one route over the other, a neighboring AS does not have the opposite preference after the local processing of the routes. Many routing policies are isotone, even if network operators are not explicitly aware of the fact. The GAU-Rexer routing policies, for instance, are isotone. Note that optimal route consistency is not synonymous with efficiency. It's the maximal number of nodes that can forego Q, does not say if there are many of them or not many of them. Okay? The aggregation strategy. So provider-independent prefixes do not have a parent in the prefix tree, and so they cannot be subject to the filtering strategy. Dragon allows nodes to create aggregation prefixes so that the provider-independent prefixes can be filtered somewhere else in the network. An aggregation prefix does not create new address space, so it's a beacon, it's not a destination, and it has to cover more than one provider-independent prefix. BGP self-organizes if more than one AS decides autonomously to generate the same aggregation prefix. Again, the exchange of messages is with standard BGP. I will go through a very simple, even a very simplistic example of the aggregation strategy. So in this example, AS4, so AS1 is a provider of AS2, who is a provider of AS3, AS3 is a provider of AS4, AS5, and AS6. AS4 originates prefix P0. That's prefix P appended with a 0. AS5 originates P10, and AS6 originates P11. Okay. P0, the address space of P0 together with P10 and P11 make the address space of P. Nodes AS1, AS1, 2, and 3, they elect customer routes to reach each of these prefixes. Okay? In order to generate an aggregation prefix, you cannot create new address space. You have to have at least 2 covered prefixes, and you have to elect a customer route for each of the covered prefixes. So AS3 is under these conditions. AS3 can create an aggregation prefix. Suppose it does create the aggregation prefix P. Then it announces the aggregation prefix to all its neighbors. AS2 will elect a customer P route and the customer route as well for all the more specific prefixes. If it applies the filtering code, it will be able to filter all the more specific prefixes, so that AS1 will be even oblivious of these prefixes. AS4, AS5, and AS6 will also be able to filter the more specific prefixes, except the ones that they generated. Again, in the general case, the aggregation prefixes apply to the prefixes in the trees that are at the roots. The system self-organizes if there are more than one node originating the same aggregation prefix. And we even have optimal, under this magic of the isotonicity property, if routing policies are isotone, then the origins are optimal in the sense that they maximize the filtering possibilities elsewhere in the network. Some performance results. We have used the annotated inferred topologies provided by CADA. These topologies give for every link, classify every link as either customer provider or peer-peer. Accordingly, we have used the Gauss-Wexford routing policies. We have also used the IPv4 prefixes to AS mappings provided by CADA. Dragon can be evaluated along many different dimensions. I've chosen here just results for the FIB filtering efficiency, which is the normalized amount of reduction brought by Dragon to the forwarding tables of an AS. Okay. I consider the case of basic Dragon, which consists just of the filtering strategy, and we saw that every AS have a FIB filtering efficiency of at least 47%. So they forego at least 47% of the prefixes. And 87% of the ASs reach the maximum possible filtering efficiency of 49%. With aggregation prefixes, every AS forgoes at least 69% of the prefixes, with 87% of the ASs, again the same number, attaining the maximum filtering efficiency of 79%. In conclusion, Dragon is a BGP add-on to scale the internet routing system. Dragon can be deployed incrementally, and it reduces the amount of forwarding state by approximately 80% if you take full Dragon into account. But we think that Dragon is more fundamentally a solid framework to reason about route aggregation. It's based on a solid theory that encompasses all types of routing policies. So it's on solid ground, we think. Okay, we have a website. Please come and visit us, and I'll be happy to take any questions.
Phil Rosenthal from IS Prime. So, from my perspective, if you're an endpoint on the internet and you're not providing transit to anyone.
Could you please speak a bit louder for that?
Phil Rosenthal from IS Prime. So, from my perspective, if you're an endpoint on the internet and you're not providing BGP transit, this should work as you described. But if you're providing transit, you end up with a problem where if you're not announcing a more specific route to a customer of yours, and your competitor is, because in their case they see different paths, your competitor is going to take that traffic and not you. So it seems like because BGP always will pick the most specific as the ultimate rule breaker, something would need to break that mechanism also.
Right. So if you are not announcing the more specific to one of your customers and the other provider is announcing, of course the traffic will go that way. But then the customer, I would argue, also have an incentive to filter as well and spread or balance the traffic both ways. That is one of our arguments here.
Yeah, that requires a lot of micro policies around the internet, though. I mean, it would need to be automated for everyone to really take that on. So.
Okay. Matt Petak, Yahoo. I know I'm pretty dumb, so I'm just a little slow on this, but when you were talking about the aggregated route generation, you had 3 ASs at the bottom, all feeding up into AS3, and then AS2 was magically generating an aggregated route P. Can you just help me understand what the AS path would look like on that route coming, that P route that's generated?
You're asking me, why is it generating the P route?
No, I'm asking, what would the AS path look like? Would AS2 simply state that it was the origin? Would AS2 claim that 3 was the origin? What AS number would show up as the origin of that P route?
Well, the origin would be AS3.
So AS2 would be telling the world, hey, AS3 has this route, even though AS3 doesn't think it has that route.
Well, AS3 will function here as a beacon. It's not creating new address space. I mean, you are right on your comment. But AS3's function is for the benefit of the internet. So it's a beacon there. It's not creating address space. But it's true that the origin will be S3.
Okay, I suspect that you might find ISPs are a little concerned if somebody else tells the world, hey, guess what? I'm gonna create a prefix that he doesn't think exists, and I'm gonna tell the rest of the world that it was his. I think this is an interesting idea. I just think the idea of speaking up for somebody else on their benefit without necessarily having their collaboration might not be well received. But it's a good theory. Thank you.
Márcio Deus from Globnet and University of Brasilia. It's a very interesting idea, but I'd like just to...
Would you mind speaking a bit louder? I'm so sorry.
Yeah, for sure, for sure. Márcio Deus from University of Brasilia and Globnet. It's a very interesting idea. I'd just like to, for sure, let you know that in South America, because our asymmetric traffic way to receive traffic, we really use a lot the more specific information about routing to make traffic engineering, because we are, in most of part, we are very small ASs, and we want to spread our more specific routing information to the big ASs to try to make some kind of reverse path traffic control. So in this way, my question to you is, did you analyze the possibility when dealing with not with internal